In the previous lecture, I have started discussing how to obtain the UMP unbiased test for the variance of a normal population when both the parameters are unknown. So, the model, let me recollect here. We considered a random sample from normal mu sigma square distribution. The joint density function of x 1 x 2 x n I am expressing in the form of a 2 parameter exponential population c theta nu e to the power theta u x plus nu t x, where I am defining theta as minus 1 by 2 sigma square, u is equal to sigma x I square, nu is equal to n mu by sigma square and t is equal to x bar. I have shown that the 4 testing problems H 1, H 2, H 3 and H 4, they are equivalent to testing about sigma square. So, and they are having the same form, that is because theta naught theta is equal to minus 1 by 2 sigma square, this is an increasing function of sigma square. Therefore, all the inequalities or equalities are maintained, that is theta less than or equal to theta naught is equivalent to sigma square is less than or equal to sigma naught square, if I define theta naught to be equal to minus 1 by 2 sigma naught square. Similarly, if I define theta 1 is equal to minus 1 by 2 sigma 1 square and theta 2 is equal to minus 1 by 2 sigma 2 square, then theta less than or equal to theta 1 or theta greater than or equal to theta 2 is equivalent to sigma square less than or equal to sigma 1 square or sigma square greater than or equal to sigma 2 square. And similarly, theta 1 less than theta 2 is equivalent to sigma 1 square less than sigma square less than sigma 2 square, and so on. Therefore, the by theorem 2, which I discussed yesterday, UMP unbiased tests exist for all the 4 testing problems. So, let me take up H 1 versus K 1. Okay. So, now we are dealing with the continuous distributions. Therefore, in the test function, the term gamma naught, this term I need not write, because the probability of this u is equal to C naught t will be 0. So, we do not write this, rather we incorporate it in either this part or here. So, if I take this to be 0 for example, then this will be incorporated here. So, the UMP unbiased test, say phi 1 is reject H naught H 1 if u, that is sigma x I square, is greater than or equal to a function of t, that is x bar, and this C x bar is determined from probability of sigma x I square greater than or equal to C x bar given x bar is equal to, say, small x bar is equal to alpha, when theta is equal to theta naught or say sigma square is equal to sigma naught square. Now, note here this needs the conditional distribution of sigma x I square given x bar, which is slightly inconvenient. However, here we can apply a trick here. This is equivalent to saying probability of sigma x I square minus n x bar square greater than or equal to some other function, say C naught x bar given x bar is equal to x bar is equal to alpha at sigma naught square. Now, this sigma x I minus x bar whole square, this is independent of x bar. If this is independent of x bar, this term will become free from. So, C naught will become free from x bar. Now, this is what we had required here. So, we can say sigma xi minus x bar whole square by sigma naught square greater than or equal to say k. So, since sigma xi minus x bar whole square by sigma naught square, this follows chi square distribution on n minus 1 degrees of freedom when sigma square is equal to sigma naught square. So, this k will become equal to upper 100 alpha percent point of chi square distribution on n minus 1 degrees of freedom. So, we have got an exact test. So, this is the reject H 1. Okay. We are getting the level alpha test. This is UMP unbiased test. If we want to apply theorem say 3 directly, then define W is equal to H u t is equal to u minus n t square, that is equal to sigma x I square minus n x bar square, that is sigma x I minus x bar whole square. Then W and u are independent. So, for sigma square is equal to sigma naught square, also they will be independent, and W is increasing in u. So, by theorem 3, the UMP unbiased test is phi 1 reject H 1 if W is greater than some C, where probability of W greater than C at sigma naught square is equal to alpha, which is the same, which again gives C, that is W by sigma naught square greater than C by sigma naught square, that is equal to chi square n minus 1 alpha. The tests for H 2 and H 3 can also be derived in a similar way. Let me write for one of them. For H 2 versus K 2 problem, UMP unbiased test is reject H 2 if C 1 is less than W is less than C 2, and you will have probability of C 1 by sigma 1 square less than or equal to W by sigma 1 square less than C 2 by sigma 1 square is equal to alpha, when sigma 1 square is the true parameter value, and also when sigma 2 square is also coming. So, these two conditions will give the value of C 1 and C 2. For H 4 versus K 4 problem, now here UMP unbiased test is reject H 4 if W is less than C 1 or W is greater than C 2, or accept if C 1 is less than or equal to W less than or equal to C 2. You will have probability of C 1 less than or equal to W less than or equal to C 2 at sigma naught square is equal to alpha, and there will be another condition, that is expectation of W 1 minus phi 4, let me call it phi 4 W at sigma naught square is equal to 1 minus alpha expectation sigma naught square w. Now, in this w you consider the division by sigma naught square. So, for example, here this will become sigma naught square, this becomes sigma naught square, this becomes sigma naught square. So, here also you consider division. So, w by sigma naught square follows chi square n minus 1. So, expectation of w by sigma naught square is equal to n minus 1. So, this condition, second condition will become then expectation of, well, you can write integral 1 by n minus 1 y of chi square n minus 1 y dy. This is the density function of a chi square variable on n minus 1 degrees of freedom from C 1 by sigma naught square to C 2 by sigma naught square is equal to 1 minus alpha. And this condition is actually equal to chi square n minus 1 density from C 1 by sigma naught square to C 2 by sigma naught square is equal to 1 minus alpha. So, these two conditions will give the value of C 1 and C 2. I have demonstrated here that we can apply theorem 3, that means, we can suitably define the function w such that we are getting the UMP unbiased test for the variance testing. Let us also consider now the testing for the mean. Testing for mean in a normal population. Let us go back to the original expression that I wrote for the joint density of normal distribution of x 1 x 2 x n here. Here I took theta to be minus 1 by 2 sigma square and nu to be n mu by sigma square, and therefore, I was able to test for sigma square. If I want to test for mu, then I have to change the role of theta and nu here. So, then I write here. So, model is the same, that means, x 1 x 2 x n follows normal mu sigma square. Now, in this case, we rewrite the joint PDF of x 1 x 2 x n as e to the power minus n mu square by 2 sigma square e to the power n mu x bar by sigma square minus 1 by 2 sigma square sigma x I square, and this I call C star theta nu e to the power theta t theta u plus nu t. Now, here I have changed the roles. Here theta is equal to n mu by sigma square, nu is equal to minus 1 by 2 sigma square, u is equal to x bar, t is equal to sigma x I square. Let me restrict attention to H 1 and H 4. So, H 1 would be theta less than or equal to 0. Okay. If I want to test for, say, mu is equal to mu naught, then this is equivalent to that I can take mu naught to be 0 without loss of generality. If I take mu less than or equal to mu naught, or and so on, mu greater than mu naught or mu not equal to mu naught, because we can shift all the observations by mu naught. So, my testing problem can be then written as, so we may write the testing problems as, so for example, if I am looking at say h 1 theta less than or equal to 0 versus k 1 theta greater than 0, then this is equivalent to say h 1 star mu less than or equal to 0 versus k 1 star mu greater than 0. Similarly, if I consider say h 4 theta is equal to 0 versus k 4 theta is not equal to 0, then this is equivalent to h 4 star theta mu is equal to 0 versus k 4 star mu is not equal to 0. So, let me UMP unbiased tests will exist. Okay? UMP unbiased tests exist for both the problems. So, now let us consider say for h 1 versus k 1 problem. For this problem, I define w is equal to u by square root t minus n u square, that is x bar divided by root sigma x I square minus n x bar square. So, this is nothing but x bar divided by square root sigma x I minus x bar whole square. If you see this carefully, then w is increasing function of u, and if we consider the distribution of w and t, the distribution of t when mu is equal to 0, then that is free from mu, and if I consider the distribution of w, that is also free from when mu is equal to 0, it is free from u. So, let me just write it here. The distributions of w and t are independent when mu is equal to 0. So, by theorem 3, UMP unbiased test for h 1 versus k 1 is reject h 1 if w is greater than or equal to c. Now, in order to look at the distribution of w, see the w is x bar divided by root sigma x I minus x bar whole square. So, we may consider here x bar follows normal 0 sigma square when mu is equal to 0. So, x bar by sigma follows normal 0 1. If I look at x bar divided by root sigma x I minus x bar whole square by sigma square, that follows chi square n minus 1, and these two are independent. These two are independent. So, if I look at the ratio x bar by sigma divided by square root sigma x I minus x bar whole square by sigma square into n minus 1, that will follow t distribution on n minus 1 degrees of freedom. There is a small mistake here, this will be divided by n. So, here I will have to put square root n. So, this is square root n, that means it is equal to square root n into n minus 1 w. So, we can modify, we can define this as say let me call it say S. Okay. So, when mu is equal to 0, S follows T distribution on n minus 1 degrees of freedom. So, the region W greater than or equal to C is equivalent to S greater than or equal to some k, where probability of S greater than or equal to k when mu is equal to 0 should be equal to alpha. That means, k value is nothing but T n minus 1 alpha, that is the upper 100 alpha percent point of the T distribution on n minus 1 degrees of freedom. So, the exact test has been derived. If I use the notation which I have developed here, then the test is reject H 1 if root n into n minus 1 W is greater than or equal to T on n minus 1 alpha. So, this is the exact test. We may include equality or we may not include equality here at this point, it does not make any difference. If you look at this function here that I have defined, u divided by square root t minus n u square, this is not a linear function of t, a linear function of u, although it is increasing in u, but it is not linear. So, if I want to test the hypothesis H 4 versus K 4, I cannot use this. So, for that I define another function. For H 4 versus K 4, we define W is equal to u divided by square root of t. Now, this is linear in t, linear in u, increasing in u, and the distribution of W is independent of t when mu is equal to 0. So, the conditions that I wrote in H 4 versus K 4 test for the test function phi 4, let us recollect those conditions. The conditions I wrote as the form of the phi 4 function, the condition that expectation of phi 4 should be equal to alpha at theta naught, also expectation of theta naught W phi 4 W, that should be alpha times expectation of phi 4 W. These conditions 7, 8, 9, they should be satisfied here. So, the conditions 7, 8, 9 are therefore satisfied. Okay, we note here the distribution of W is symmetric about 0 when mu is equal to 0. That is important here. The condition 7, 8, 9 are therefore satisfied for the rejection region modulus W greater than or equal to C, and probability of modulus W greater than or equal to C is equal to alpha. So, if we define say small t is equal to square root n into n minus 1 W divided by square root 1 minus n W square, then modulus t is increasing in modulus W. So, this region is then equivalent to modulus t greater than or equal to k, and the distribution of t is nothing but t distribution on n minus 1 degrees of freedom when mu is equal to 0. So, we can choose then this k as t n minus 1 alpha by 2. This is the famous t test, which was initially derived by Gosset in 1907. Of course, he did not consider it as a UMP unbiased test, he considered it as a likelihood ratio test only. But here we are able to derive the exact test when sigma is unknown. So, this is testing for the mean here. Now, I will consider two sample problems, that means, we consider testing for comparison of means and variances in two normal populations. Remember, here our aim is to consider the UMP unbiased test. Therefore, we will write the joint density in the form of a multi-parameter exponential family. So, let us consider say x 1, x 2, x m a random sample from normal mu 1 sigma 1 square and y 1, y 2, y n a random sample from normal mu 2 sigma 2 square. So, I assume that x and y are independently collected, the two random samples are independent. Now, let us take the first problem, comparison of say variances. That means, I need to test something like sigma 1 square is equal to sigma 2 square against sigma 1 square is not equal to sigma 2 square, sigma 1 square is less than or equal to sigma 2 square, or sigma 1 square is greater than sigma 2 square, etcetera. That is the comparison. Now, keeping into view that the sigma parameter in the normal distribution is actually a scale parameter. When we are considering the scale, it will be beneficial if I consider the ratio. That means, the hypothesis sigma 1 square is equal to sigma 2 square, I can express as sigma 2 square by sigma 1 square is equal to 1, or sigma 2 square by sigma 1 square, sigma 1 square by sigma 2 square is equal to 1, etcetera. Similarly, if I say sigma 1 square is less than or equal to sigma 2 square, I can express it as sigma 2 square by sigma 1 square less than or equal to 1, greater than or equal to 1, etcetera. That means, I take the ratio, because in the form of the density that I have expressed in the normal distribution, you can see here this is appearing in the denominator. So, taking the difference will not be easy, in fact, it will be extremely inconvenient. Therefore, if I take the ratio, I will be able to express it in a proper form. So, now let us look at the hypothesis testing problem such as say H 1. I will write slightly general hypothesis sigma 1 is sigma 2 square by sigma 1 square less than or equal to some say tau naught against say k 1 sigma 2 square by sigma 1 square greater than tau naught, and similarly we may consider say H 4 sigma 2 square by sigma 1 square is equal to tau naught against k 4 sigma 2 square by sigma 1 square is not equal to tau naught. So, in order to write it in the form of a required desired multi-parameter exponential family, let us write down the joint PDF of x and y. So, that is equal to f x y mu 1 mu 2 sigma 1 square sigma 2 square, that is equal to so there will be some terms basically if I write in full it will become 1 by sigma 1 root 2 pi to the power m sigma 2 root 2 pi to the power n e to the power minus m mu 1 square by 2 sigma 1 square minus n mu 2 square by 2 sigma 2 square, and then e to the power minus sigma x I square by 2 sigma 1 square minus sigma y j square by 2 sigma 2 square plus m mu 1 x bar by sigma 1 square plus n mu 2 y bar by sigma 2 square. Here straightforwardly this is a 4 parameter exponential family, as I have described in the example in one of the previous lecture where I was applying the Bosco's theorem. But the problem here is that if I straightforwardly write it as a 4 parameter exponential family, I can test about either sigma 1 square or about sigma 2 square or about mu 1 or about mu 2, which is not our aim. So, we reparameterize it. So, this coefficients I put it as C of theta nu, and this I write as e to the power 1 by 2 sigma 1 square tau naught minus 1 by 2 sigma 2 square into sigma y j square minus 1 by 2 sigma 1 square sigma x I square plus 1 by tau naught sigma y j square plus m mu 1 by sigma 1 square x bar plus n mu 2 by sigma 2 square y bar. Here I am taking theta to be 1 by 2 sigma 1 square tau naught minus 1 by 2 sigma 2 square. So, u is equal to sigma y j square. Nu 1 is equal to minus 1 by 2 sigma 1 square. So, T 1 is equal to sigma x I square plus 1 by tau naught sigma y j square. Nu 2 is equal to m mu 1 by sigma 1 square. So, T 2 is equal to x bar. Nu 3 is equal to n mu 2 by sigma 2 square. So, T 3 is equal to y bar. So, if I am considering the testing problem, say H 1, that is sigma 2 square by sigma 1 square less than or equal to tau naught, we can express it as 1 by tau naught sigma 1 square, and I divide here. So, 1 by sigma 2 square, and I put 2 here. So, this will become plus, this will become minus. So, if I take sigma 2 square in the denominator here and I bring it to the left hand side, this becomes less than or equal to 0. So, this theta term that I am having, this is equivalent to less than or equal to 0. So, this will be equal to theta is equal to 0. So, H 1 sigma 2 square by sigma 1 square less than or equal to tau naught, this is equivalent to say H 1 star theta less than or equal to 0. And similarly, this H 4, that is sigma 2 square by sigma 1 square is equal to tau naught, this is equivalent to H 4 star theta is equal to 0. So, we can derive the UMP unbiased tests. However, those UMP unbiased tests, if I use theorem 2, they will be conditional tests of u given T 1, T 2, T 3, u given T 1, T 2, T 3, u is this. So, this conditional distribution will be quite complicated, even when I am taking say sigma 2 square by sigma 1 square is equal to tau naught. So, this will be quite complicated form here. So, what we do? We apply theorem 3. To apply theorem 3, I define function w as an increasing function of u, and the distribution of w should be free from T 1, T 2, T 3. So, we consider like this, define W is equal to h of u T1 T3, that is equal to m minus 1 by n minus 1 sigma 1 square by sigma 2 square u minus n T3 square divided by T1 minus u by delta tau naught minus m T2 square. It is actually equal to sigma yj minus y bar square divided by n minus 1 sigma 2 square divided by sigma xi minus x bar whole square divided by m minus 1 sigma 1 square. So, sorry. So, W is increasing in u, the distribution of W does not depend on mu 1, mu 2, sigma 1 square, sigma 2 square. Actually, this is F distribution on n minus 1, m minus 1 degrees of freedom. So, since the distribution of W does not depend upon the parameters, and when theta is equal to 0, T is sufficient. When theta is equal to 0, T is, that is T, T1, T2, T3, that is sufficient and complete. So, by an application of Bosco's theorem, W and T are independent when theta is equal to 0. Remember that for testing H1 and H4 both, I need the independence when theta is equal to 0, that is satisfied here. So, by theorem 3, a UMP unbiased test for H1 versus K1 is reject H1 if W is greater than or equal to C, and probability of W greater than or equal to C when theta is equal to 0, that is equal to alpha. So, C is given by the point on F distribution, that is upper 100 alpha percent point of F distribution on n minus 1, m minus 1 degrees of freedom. This should be n minus 1, m minus 1. Firstly, it is n minus 1 in the numerator, because the way I have defined here this function, in the numerator the degrees of freedom for chi square is n minus 1, and in the denominator it is m minus 1. So, we are getting an exact test here using the theory of unbiased tests here for testing for the comparison of the variances. Like I have put here sigma 2 square less than or equal to sigma 1 square here. If I consider say sigma 1 square is equal to sigma 2 square versus the inequality, then this function will not be useful, because this is not linear in tau and linear in u. So, we need to define another function which is related to this. For H4 versus K4, we define say W star is equal to H u t, that is equal to u minus n T3 square divided by tau naught divided by T1 minus m T2 square minus 1 by tau naught n T3 square, that is equal to 1 by tau naught sigma yj minus y bar square divided by sigma xi minus x bar square plus 1 by tau naught sigma yj minus y bar square. Now, W star is linear in u, and of course, it is increasing when theta is equal to 0. the distribution of W star does not depend on nu 1, nu 2 and nu 3. The parameters that I defined here when I wrote in this particular fashion, nu 1 was minus 1 by 2 sigma 1 square, nu 2 was this and nu 3 was n mu 2 by sigma 2 square. So, that is true here, that the distribution of this thing does not depend on this when theta is equal to 0. So, W star and T are independent when theta is equal to 0. So, UMP unbiased test for H 4 versus K 4 is given by reject H 4 if W is less than W star is less than C 1 or W star is greater than C 2. Now, to determine C 1 and C 2, the conditions are, let me call this test say phi 4, then you have expectation of 1 minus phi 4 W star at theta is equal to 0, that is equal to 1 minus alpha, and expectation of W 1 minus phi 4 star phi 4 W star, that is equal to 1 minus alpha times expectation of W star at 0. Now, when theta is equal to 0, the distribution of W star is actually a beta distribution on n minus 1 by 2 and m minus 1 by 2 degrees of freedom. That is this function when I am assuming sigma 2 square by sigma 1 square is equal to tau naught, then this is actually having, because it is actually in the numerator a chi square divided by sum of two chi squares and they are independent. So, this is a beta distribution actually n minus 1 by 2 and m minus 1 by 2. So, this condition is actually then determined from, if I write the density of beta as say beta n minus 1 by 2 m minus 1 by 2 y dy, then from C 1 to C 2 this should be equal to 1 minus alpha. And the second condition we can simplify, because expectation of W star is actually n minus 1 by m plus n minus 2. If we utilize that, then this condition can be transformed to g n plus 1 by 2 m plus 1 by m minus 1 by 2 y dy from C 1 to C 2 is equal to alpha 1 minus alpha. Now, this is actually the density of, that means I am using this beta say p q y, this is density of a beta distribution with parameters p and q. Then these two conditions can be used to determine the coefficients C 1 and C 2. For convenience, we are generally taking alpha by 2 point and 1 minus alpha by 2 point on the f m minus 1 n minus 1 degrees of. Now, let me consider comparison of two means of normal populations. Comparing means of two normal populations. That means, we want to test whether mu 1 is equal to mu 2, mu 1 less than or equal to mu 2 or mu 1 is greater than mu 2. We assume here that sigma 1 square is equal to sigma 2 square is equal to sigma square. This is of course unknown here. The joint density function of x and y as we wrote earlier. Now, this has to be written for modified form. That means, when sigma 1 square is equal to sigma 2 square, the terms will be combined. Let me go back to the original form here. In this term, sigma 1 square, sigma 2 square are same. So, here sigma x I square and sigma y j square will get combined, and this one also will have common denominator. So, this term will also get combined. Now, when they get combined and I want to get mu 1 minus mu 2 for comparison of mu 1 mu 2. So, we rewrite in the following fashion. So, let me give this form here is written as, because I am not writing the original term again and again, I have already written it several times. So, I am considering this a function of mu 1 mu 2 and sigma square e to the power theta u plus nu 1 t 1 plus nu 2 t 2, where, so this is theta nu now, nu 1 nu 2, theta nu 1 nu 2, where theta I am defining to be mu 2 minus mu 1 divided by sigma square m plus n into m n. Then nu 1 is equal to m mu 1 plus n mu 2 divided by m plus n sigma square, nu 2 is equal to minus 1 by 2 sigma square, u is equal to y bar minus x bar, t 1 is equal to m x bar plus n y bar, t 2 is equal to sigma x I square plus sigma y j square. So, if I consider the hypothesis h 1 theta less than or equal to 0, this is equivalent to h 1 star say mu 1 less than or equal to mu 2. Similarly, if I consider theta is equal to 0, this is equivalent to theta not equal to, that is mu 1 not equal to mu 2. So, once again we have the UMP unbiased tests here. So, UMP unbiased tests can be derived for H 1 versus K 1 and H 4 versus K 4 using theorem 3. So, if I consider the problem H 1 theta less than or equal to 0 versus K 1 theta greater than 0, we define the function w, that is as u divided by t 2 minus t 1 square by m plus n minus m n by m plus n u square. Now, this function is actually y bar minus x bar divided by square root of sigma x I minus x bar whole square plus sigma y j minus y bar whole square. H is increasing in u, that can be easily checked here. When theta is equal to 0, now let us look at the distribution theory here. What are the distributions here? X bar will follow normal mu 1 sigma square by m, y bar follows normal mu 2 sigma square by n. The distribution of y bar minus x bar is normal mu 2 minus mu 1 sigma square 1 by m plus 1 by n. So, when theta is equal to 0, y bar minus x bar will follow normal 0 m plus n by m n sigma square. The distribution of y bar minus x bar is free from theta. Also, the distributions of sigma xi minus x bar whole square by sigma square. This follows chi square distribution on m minus 1 degrees of freedom. The distribution of sigma yj minus y bar whole square by sigma square, that follows chi square distribution on n minus 1 degrees of freedom. So, these are all having distributions independent of theta. So, when theta is equal to 0, the distribution of W does not depend on what is nu 1 and nu 2 here. Nu 1 involves mu i's and sigma square, nu 2 involves sigma square. If we consider this function, if I take divided by sigma and here this thing divided by sigma square. So, you can easily see that the distribution of W is also free from sigma. So, this does not depend on nu 1 and nu 2. So, when theta is equal to 0, T 1 T 2 is a complete sufficient statistic here. So, when theta is equal to 0, T 1 T 2 is complete and sufficient. So, Basu's theorem is applicable here. Basu's theorem gives that when theta is equal to 0, W and T 1 T 2 are independent, and therefore, we are in a position to write down the UMP. So, UMP unbiased test for H 1 versus K 1 is reject H 1 if W is greater than or equal to C. Now, let us look at the distribution part of W. So, we have already seen here that y bar minus x bar, this follows normal 0 m plus n by m plus n by m n sigma square when theta is equal to 0. So, we adjust this term here, we get here y bar minus x bar divided by root 1 by m plus 1 by n divided by square root sigma x I minus x bar square plus sigma y j minus y bar square divided by m plus n minus 2. Let us define this as say t. Then this is t distribution on m plus n minus 2 degrees of freedom when theta is equal to 0. Therefore, I can choose this term W as t greater than or equal to k, and t will be m plus n minus 2 alpha, the upper 100 alpha percent point of the t distribution on m plus n minus 2 degrees of freedom. So, you can see here this is the pooled sample variance formula here that we are getting here. In fact, we can write this term as root m n m plus n by root m n by m plus n y bar minus x bar divided by s p, where s p square is actually sigma x I minus x bar whole square plus sigma y j minus y bar whole square divided by m plus n minus 2. So, we are comparing, the test is reject H 1 if this is greater than t m plus n minus 2 alpha. We have an exact UMP unbiased test. Now, let us also look at the H 4 problem. For H 4 versus K 4, this function will not be useful, because this function is not linear in U. So, I modify, we can consider W star is equal to U divided by square root T 2 minus T 1 square by m plus n. this is linear in U, and this function, if you see, actually it is y bar minus x bar divided by square root sigma x I square plus sigma y j square minus 1 by m plus n sigma x I plus sigma y j whole square. So, this term is free from mu 1 mu 2 sigma 1 square sigma 2 square when mu 1 is equal to mu 2. So, distribution of W star is independent of T 1 T 2. So, and also W star has distribution symmetric about 0 when mu 1 is equal to mu 2. So, UMP unbiased test is based on W star greater than or equal to C, that is the rejection region. Now, what we can do? We can consider, say, W, that is W star divided by root 1 minus m n by m plus n W star square. This is increasing in W star. So, we can again write the rejection region as modulus of T, which I defined in the previous case, I am sorry, this is T. So, in terms of this T, which was having m plus n minus 2 degrees of freedom, we can write here T greater than or equal to T m plus n minus 2 alpha by 2, where this T is actually y bar minus x bar root m n by m plus n divided by S p. In this today's lecture, I have been able to give UMP unbiased tests for parameters testing problem for one sample problem from normal distributions, also for the comparison of parameters for two sample problems. That means, when we are having two normal populations, then for comparison of the variances I am having UMP unbiased test, for the comparison of the means I am having unbiased test, UMP unbiased test. One point which should be noted, when I was considering comparison of the means, I have taken sigma 1 square is equal to sigma 2 square. When I gave the derivation, it was clear that it was helping, because in the denominator, in the exponent, in the joint density, that sigma square term was getting combined. So, the terms were adjusted. However, if I do not make this assumption that sigma 1 square is equal to sigma 2 square, then I will not be able to adjust these terms. So, when sigma 1 square is not equal to sigma 2 square, that is unknown, the problem of comparing means, this is called Variance-Fisher problem. In fact, it can be shown that there is no exact test, no exact UMP unbiased test for this problem. Approximate tests are available, which are actually, you can say, approximately T distribution is there, which are provided by Smith, Satterwhite and Welch, etc. We are not discussing it here, because in this particular course, I have actually given you the derivations of the exact test. The theory that I have developed is using the Neyman-Pearson theory. The concept started from the simple versus simple hypothesis. We had considered the most powerful test for a fixed size. Then we extended that theory to UMP unbiased test. Initially, we considered the families of distribution with monotone likelihood ratio. Later on, we restricted attention to one parameter exponential family. For I defined 4 special kind of hypothesis, H1, H2, H3 and H4. For H1 and H2, we were having UMP test. For H3 and H4, we got UMP unbiased test. Whereas, when we considered multi-parameter exponential family, all of the testing problems reduced to we are getting the UMP unbiased test. In the next lectures, I will introduce another method of derivation of the test called likelihood ratio testing procedures, which is also a natural procedure. I will be describing those tests in detail in the following lectures.